In this video, we will make a recap on the concept you have learned in this course on quantum information. The basic unit of information in quantum computing is called quantum bit or qubit. A qubit can be in state 0 or state 1 as a classical bit. However, a unique feature of qubits is that they can be in a superposition of the 0 and the 1 states. This superposition is described by a linear combination of both states with coefficients alpha and beta. These coefficients define the probability that the state is in the 0 or the 1 state. When measuring a qubit in the set basis, the probability of getting a result 0 is given by the absolute value of alpha squared, and the probability of measuring a 1 is given by the absolute value of beta squared. The coefficients satisfy the Born rule. That is, the sum of the magnitude squares must add up to 1. Note that the outcome of a measurement is random and a binary value either 0 or 1 is obtained. In addition, measuring a qubit in a certain basis projects the qubit state onto one of its endgame states, destroying its superposition and therefore changing its state. This is called projective measurement. Qubit states can also be modified by applying a quantum gate. For instance, an X gate or bit-flip gate will bring qubit state 0 to 1, and as you may already know, it is equivalent to a rotation of pi around the x-axis of the Bloch sphere. So far, we have been talking about a single qubit, but how to describe the joint state of a quantum system consisting of several qubits? As we have seen, the state of an n-qubit register can be described as a superposition of the 2 to the n possible combinations of the n-qubit registers. As in single qubit states, the sum of the probability amplitudes squared must be 1. For instance, the state of 2 qubit registers is a superposition of all possible combinations of the first qubit register being 0 or 1 and the second being 0 or 1. It can be written as a linear combination of 4 states, which in the computational basis of 2 qubits will simply be 0, 0, 0, 1, 1, 0, and 1, 1. In order to derive this 2 qubit state, we just need to perform the tensor product of the 2 qubit registers. But what happens when measuring a qubit in this 2 qubit system? The measurement in a multi-qubit system is similar to the single qubit case. The state of the qubits that we measure gets projected to the corresponding eigenvector, and the other qubit, the one we haven't measured, is left in the state that it was accompanying. Let's remind now how to manipulate multi-qubit registers using quantum gates. The gates applied to an n-qubit register will be given by a unitary 2 to the n dimensional matrices. For instance, the resulting matrix of applying an X gate to the top qubit and a Hadamard to the bottom one can be calculated by the tensor product of the individual gates. In addition, remember that gates acting on n qubits also exist. One of the most popular ones is the control NOT or CNOT gate. This gate flips the target qubit if the control qubit is in the 1 state. The CNOT gate allows us to create entanglement, another important property in quantum computing. If we apply a CNOT to the +0 state, we create the state 0, 0 plus 1, 1, which you might recognize as one of the Bell states. By choosing the appropriate input states for both qubits, we can create the 4 Bell states. Qubits composing a Bell state are entangled because their joint state cannot be written as a tensor product of the states of the individual qubits. Bell states are key in quantum communication operations, such as quantum teleportation, entanglement swapping, and superdense coding. Let's briefly review how they work. In the quantum teleportation protocol, arbitrary quantum states can be transported from one place, in our case a blue party, to another, yellow one, by consuming a Bell pair and 2 classical bits. For the teleportation to take place, first a Bell state and an arbitrary qubit, the one that we want to teleport, are prepared. Then, half of the Bell state and the prepared qubit are sent to a Bell state analyzer. The result after measurement, the two classical bits, are used to perform the corresponding unitary transformation on the other half of the initial Bell state that was kept by the yellow party, recovering in this way the prepared qubit. Another fascinating quantum communication primitive is entanglement swapping or teleportation of entanglement. It allows two parties that are not directly connected to establish entanglement by consuming a Bell pair and two classical bits. It works as follows. First, the two not connected parties, blue and yellow, create Bell states. They keep one of the particles of the respective Bell state and send the other to a common intermediate station, represented by purple, which is responsible for running the Bell state analyzer. After the measurement, purple transmits the result, 2 bits, to the yellow party. It will then perform the required unitary transformation on the particle of the initial Bell state it kept in the beginning. After this operation, the joint state of the particles in possession of the blue and yellow will be entangled. Let's finally discuss the last communication protocol in this course called superdense coding. It allows to transmit two classical bits from a yellow party to a blue one by sending only one qubit. To do so, blue creates a Bell state, and it keeps half of it and sends the other half to yellow. Then, yellow determines the unitary transformations to be performed based on the 2 qubits, the message it wants to send. After that, yellow sends its half Bell pair back to blue, which runs its Bell state analyzer. Note that in this protocol, the transmission of the 2 bits has been done in a secure way, as blue and yellow use an entangled state. And with this, we can conclude our recap on the concepts of quantum information that have been introduced in this course.